The sky stopped being a background. It began to perform. On October 27, 2025, Moscow lit green in a way people had not seen before. A blazing streak tore across the night. Cameras from cars and apartment windows captured a brief, terrible brightness. For a few seconds, the city looked as if it had a wound in its atmosphere. Fragments broke off and fell away like sparks from a furnace. Within minutes, the footage spread across the world. This was not a lone incident. Earlier that year, a daylight bolide flashed over Georgia and South Carolina, bright enough to cast shadows at noon. In August, strange spirals traced the eastern U.S. sky. Each clip added to a growing pile of unexplained light. Each clip tightened a single question: what is happening above us? Some voices dismissed timing as coincidence. Others, including an analyst named Stefan Burns, argued for a pattern. The pattern tied to an interstellar visitor called 3I Atlas, first logged in July 2025 by an automated near-Earth scanner. If these mysteries have you hooked the way they have me, make sure to hit like and subscribe so you don't miss a single update as they unfold in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think is happening above us. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this. So, thank you for having our back. The object, officially catalogued as 2025 N1, moves on a hyperbolic path. It arrived from interstellar space and will leave on the same route. Its closest approach to the Sun, perihelion, fell on October 29, 2025, 2 days after the Moscow event. The coincidence of dates and the cluster of atmospheric phenomena changed the conversation from curiosity to urgency. Observations from the James Webb Space Telescope and the Very Large Telescope showed something unusual about the visitor. Its coma, the diffuse cloud around its nucleus, contained far more carbon dioxide than water vapor. Native comets usually release water as they warm. This one breathed differently. Spectra carried fingerprints inconsistent with objects formed in our solar system. It looked foreign. Orbit calculations showed no impact risk. The object would swing by, feel the sun's pull, then depart. No collision scenario existed. Still, proximity to mystery and proximity to danger are distinct. Public reaction moved faster than peer review. Images and witness accounts arrived before processed science. In Moscow, church bells rang in some neighborhoods. Social feeds choked with clips. People made stories in real time. Vision gives immediate narrative. Official caution takes time. Where official answers lagged, speculation rushed in. This film follows 4 threads. First, the natural explanations: meteors, atmospheric chemistry, ordinary physics of objects meeting air at high speed. Second, the instruments and data, how sensors translate events into numbers and images and how those outputs differ from what human eyes expect. Third, institutional behavior, how agencies communicate during moments of cosmic uncertainty. Fourth, a clearly labeled speculative experiment about orbital maneuvers and a hypothetical destination near Jupiter's moons. Wherever speculation appears, the label will stay clear. Moscow offers a case study. Multiple dashboard cameras recorded the same event from different angles. The footage shows initial brightening, fragmentation, secondary flares. Witnesses used dramatic language alien-like, green fireball, but those descriptors contain useful clues. Color links to emission spectra. Breakup patterns point to material strength and entry dynamics. Social media amplified the footage in seconds. Verified footage means multiple independent sources, matching timestamps, intact metadata. Until triangulation completes, some reports remain unverified. Professional triangulation will complete the geometry, reveal altitude, mass estimates, and entry angle. That work takes time. Why does 3I Atlas matter in this cluster? Rare phenomena attract attention. Attention creates context. This is the first interstellar object so closely observed at perihelion during a period of heightened meteor activity. The brain searches for patterns. When cultural anxiety overlaps with astronomical oddities, the result is combustible. Cluster analysis is next. Plot the locations and dates. Moscow on October 27th. The Georgia and South Carolina daylight bolide in June. Spiral lights along the East Coast in August. Add reports from the American Meteor Society, NASA's fireball logs, European tracking systems. At first glance the dots look alarming. But context shifts the view. The Earth passed through several active meteor streams during that window. The Orionids peaked around October 21st to 22nd. The Taurids rose in late October into November. Both showers produce bright fireballs. During shower overlap, detection rates climb. More cameras exist now than ever before. Dash cams, doorbell cams, phone cameras, everyday devices multiply sightings. The sky did not necessarily grow more active. Our monitoring improved. This is detection bias. Triangulation separates perception from pattern. Multiple cameras from different sites let analysts reconstruct a trajectory, altitude, and origin. The American Meteor Society and NASA's Meteoroid Environment Office correlate optical, infrared, infrasound, and radar. They determine whether a fireball aligns with a known shower or rides a unique orbit. The Moscow bolide lasted roughly 3 seconds. Green color points to nickel or magnesium emission lines. The fragmentation sequence matches a fast, stony meteoroid disintegrating under aerodynamic stress between roughly 80 and 30 kilometers altitude. Physics fits meteor, not miracle. Still, false positives exist. Rocket stages fall and spin, making spiral trails. Satellite glints mimic moving lights. Ionospheric disturbances produce luminous phenomena. The August spirals, for instance, look similar to documented rocket exhaust patterns. Similarity does not equal identity, but it demands careful comparison before asserting novelty. A simple probability exercise clarifies expectations. If quiet nights yield roughly 5 to 10 bright fireballs visible somewhere on Earth, active shower overlap multiplies that figure. Over weeks, the expected global count climbs. If actual reports match those expectations, the surge might be predicted. If counts exceed predictions substantially, closer inquiry is warranted. The obstacle is incomplete data. Detection thresholds vary by region. Media amplifies drama while ignoring mundane explanations. Professional triangulation, multi-sensor correlation, and patient verification are necessary. That work takes weeks. Social media has no such patience. 3I Atlas sits at the intersection of strange sky events and public attention. Because it is interstellar and compositionally odd, it attracts narratives. The object is not itself evidence for meteors on Earth, but its existence shapes how people interpret those meteors. Suspicion grows into story. The next thread examines why official channels move with apparent slowness and how delays shape public belief. Information friction matters. The Moscow fireball went viral within hours. Russian observatories issued statements after days. NASA's Meteoroid Environment Office posted preliminary notes later still. The gap between events and official explanation creates fertile ground for conjecture. This slowness rarely stems from malice. It stems from the mechanics of science. Images require noise removal. Ephemerides need cross-validation. Calibration is precise work. Agencies avoid premature claims that later require retraction. The internet ignores that caution. Missing frames in solar observatory imagery prompted accusations of deletion. The real cause often lies in instrument behavior. Coronagraphs operate protective modes near bright objects. Automatic exposure adjustments, saturation, and telemetry delays produce gaps. Those engineering realities look suspicious in comment sections. Ambiguous phrasing in press statements amplifies doubt. A cautious phrase like preliminary analysis sounds evasive when people hunger for answers. Rumor propagation follows a simple chain. A user clips a frame. An influencer reposts. Engagement spikes. Headline writers chase traffic. Within 48 hours, a marginal observation becomes a mainstream talking point. The loop needs no conspiracy to run. It runs on attention. The cultural spread of meanings is the next concern. Within hours of the Moscow fireball, apocalyptic hashtags trended. Wormwood surfaced on social feeds and in sermons. People invoked revelation. Podcasts and live streams dissected frames. Sentiment analysis shows fear peaking where apocalyptic traditions hold sway and curiosity dominating elsewhere. Emotional content spreads fast. Fear and wonder are high arousal reactions that trigger sharing. Historic religious narratives matter. Revelation's wormwood imagery has resurfaced whenever the sky seems to act out old prophecies. Halley's Comet in 1910 triggered panic. The Tunguska event in 1908 earned retroactive prophetic readings. Now 3I Atlas and scattered fireballs provide fresh material. The function of eschatology is psychological. It offers order to randomness. When the world feels unstable, narratives that promise shape feel soothing. Conspiracy networks stitch fragments into larger tapestries. Project Blue Beam, the old claim that elites might fake cosmic signs, reappears whenever sky anomalies proliferate. Evidence stays thin. Emotion fills the gaps. Channels with millions of followers stitch screenshots into narrative and the algorithm rewards engagement. Facts decline in priority. The ethical stakes are real. When belief turns to panic, harm follows. Past cult tragedies show how conviction about cosmic signs can cause death. Today networks speed everything. A fringe idea can find mass reach within hours. The infrastructure for mass hysteria exists. Speed and scale amplify the risk. Having tracked lights, data, and social feedback loops, the narrative returns to physics. Why do meteors glow green? How does perihelion reshape a comet? What realistic pathways exist for an interstellar object to influence Earth? The answers remain rooted in well-understood mechanisms. Color conveys composition. Ablation, the vaporization of surface material, produces light at elemental wavelengths. Nickel emits green near 520 nanometers. Magnesium gives bluish-green near 580 nanometers. Iron yields yellow-orange near 570 nanometers. Sodium produces a sharp yellow at 589 nanometers. Bright green suggests metal content consistent with common meteoritic material. Fragmentation follows predictable mechanics. Meteoroids are often aggregates with low tensile strength. Dynamic pressure, which scales with velocity squared and atmospheric density, eventually overwhelms structural cohesion. Pieces break off and flare. The Moscow sequence matches textbook bolide behavior. Satellite infrared sensors and infrasound arrays provide independent confirmations for large bolides. Daylight fireballs remain rare to witness, but expected globally at low frequency. Citizen video offers vivid images but limited geometry. Parallax errors and focal length distortions make single camera distance estimates unreliable. Multiple calibrated cameras produce science. Color alone does not prove origin. Orbital data from triangulation and velocity measurements carry stronger evidentiary weight. Next, the comet-sun interplay. Perihelion changes everything for a comet. As solar radiation heats the nucleus, volatiles sublimate. Carbon dioxide sublimes at lower temperatures than water. A CO2-rich nucleus begins outgassing at greater distances and with different behavior compared to water ice. Jets form when sublimation is uneven across the rotating nucleus. Jets create non-gravitational accelerations. Comets move under gravity and impulsive outgassing combined. Near the Sun, coronagraphs observe tails and plasma interactions, but glare and instrument saturation create blind spots. Coronal mass ejections can strike a comet's coma, producing tail disconnection and dramatic optical changes. The Sun behaves as an active agent. Could intense perihelion activity seed a dust stream that later intersects Earth? In principle, yes, but probability is low. Ejection velocities from sublimation are modest, typically hundreds of meters per second, not enough to radically alter orbits on short notice. Historical analogues exist when comet fragmentation later produced meteor showers, but geometry and timing must align precisely. If 3I Atlas shed dust during perihelion, debris would likely continue along a hyperbolic path outward, not concentrate onto Earth's orbit. Coronagraph gaps during perihelion foster suspicion, but these are operational constraints rather than proof of concealment. The next layer addresses instruments. Each sensor has a personality. JWST excels at infrared spectroscopy. It revealed the CO2-rich coma thanks to narrow emission line resolution. JWST does not provide continuous monitoring. It offers scheduled snapshots. Hubble provided high-resolution imaging but must avoid pointing too close to the Sun. Ground telescopes supply flexible follow-up but face weather and daylight limits. SOHO's LASCO coronagraphs excel near the Sun but saturate and create artifacts. Stereo spacecraft cover different lines of sight but face downlink limits. Ephemerides predict positions using gravitational dynamics. Comets experience non-gravitational forces from asymmetric outgassing. Small delta-V signatures are hard to attribute. Asymmetric jets mimic deliberate thrust. Distinguishing natural outgassing from intentional propulsion requires multiple independent instruments, a mismatch between observed timing and expected thermal forcing, and orbital residuals inconsistent with modeled outgassing. Historical cases exist where apparent anomalies resolved into natural behavior after months of data. Coronagraph artifacts confuse casual viewers. Diffraction streaks, cosmic ray hits, and compression artifacts all produce spurious features. A single frame with a strange streak is not proof. A consistent pattern across instruments with reconcilable ephemerides would be. Institutions occupy the next chapter. Agencies carry credibility concerns. A premature announcement that later retracts damages trust. At the same time, withholding information invites accusation. Planetary defense balances transparency with public calm. Security overlaps matter. Military tracking systems sometimes classify data that overlap civilian research. Universities may embargo data until publication. International collaborations often coordinate release. These bureaucratic rhythms create windows where information exists but cannot be shared publicly, fueling speculation. Speculative models of institutional behavior exist. Agencies might release partial information to gauge reaction. Doing so raises ethical concerns. Using public anxiety as an experiment would breach trust. Still, patterns of staged ambiguity appear in many institutional domains. Funding dynamics also matter. Dramatic events attract support for telescopes and missions. Agencies and advocates may emphasize mystery to boost budgets. That incentive exists, but it sits among many legitimate institutional pressures. Now the thought experiment. Imagine applying an Obarth maneuver during perihelion. Obarth mechanics exploit the fact that a burn performed where velocity peaks yields larger energy change at infinity than the same burn elsewhere. At perihelion, a brief thrust leverages gravitational velocity to produce an outsized long-term trajectory change. Interplanetary missions use perihelion burns to save propellant. If a visitor carried propulsion with limited fuel, perihelion would be the optimal adjustment moment. A small delta V at that time might bias an outbound hyperbolic trajectory toward a chosen target. Why Jupiter? Its Galilean moons present resource-rich options. Ganymede offers size, a weak magnetic field, and substantial ice. Europa holds a subsurface ocean and chemical potential. Callisto offers relative stability and lower radiation exposure. Io provides volatile minerals but extreme volcanism. A precisely timed burn from perihelion could bias a path toward Jupiter for a potential encounter months later. Numbers are tight. Required delta V depends on initial trajectory, desired intercept, and propulsion efficiency. Plausibility exists in physics, but probability remains extremely low. Assigning illustrative probabilities expresses epistemic humility. The likelihood an interstellar object proves artificial sits orders of magnitude below 1%. The conditional chance it would perform a directed OBTH burn toward Jupiter shrinks further. These estimates remain heuristic placeholders. The null hypothesis remains the default. 3I Atlas is a natural interstellar body. Rejecting that baseline requires positive evidence. Non-gravitational accelerations inconsistent with gassing, engineered emissions, or trajectory changes violating physical constraints would be needed before abandoning the natural explanation. Nothing so decisive has emerged. Technology marches forward. Quantum timing networks reach picosecond precision. Entangled photons and optical lattice clocks enable synchronization across hundreds of kilometers with coherence that collapses previous timing uncertainty. For transient astronomy, better timing tightens triangulation. Meteor tracking moves from meter to meter range precision. Coherent multi-station interferometry with quantum clocks promises optical baselines rivaling the separation between observatories. That resolution would image nuclear structure of comets at distances once impossible. With timing precision, small delta V events tie directly to thermal forcing or to unexplained impulses. As measurement uncertainty falls, the space for speculation shrinks. Artificial intelligence already reshapes discovery. Autonomous transient pipelines scan terabytes nightly. The Vera Rubin Observatory's anomaly triage engines run continuously. Machine learning models flag, classify, and trigger follow-up without initial human review. These systems find patterns faster than any human network. They accelerate discovery but introduce new failure modes. Algorithms trained on known classes misclassify novel events. False positives propagate through an ecosystem of alerts, social media, influencers, and mainstream outlets before human verification completes. A single flagged anomaly can create a cultural event within hours, long before spectroscopy or multi-instrument confirmation resolves its true nature. A plausible cascade looks like this. Machine detection at hour 0. Automated alert within the first hour. Social sharing and influencer amplification within a few hours. Media coverage before professional verification. Correction follows days later. By then, narrative momentum resists correction. Policy choices emerge, require human verification for high-impact alerts, implement multimodal consensus before broadcast, annotate provenance and confidence. Each mitigation introduces delays that researchers resist for scientific agility. Yet the alternative is a system optimized for speed at the cost of accuracy. Solar science yields additional context. Solar Orbiter's polar pass in September 2025 revealed magnetic structures more chaotic than models predicted. The Sun, moving toward solar maximum expected near late 2025 to early 2026, grew more active. Spikes in solar flares and coronal mass ejections altered the heliospheric environment. During mid-September through October, the Sun produced multiple medium and strong flares and several CMEs. These disturbances reached Earth and changed ionospheric conditions. Auroras appeared at unusual latitudes. Solar activity matters for comets and for observation. Coronal gusts interact with a comet's coma. Ion tails may disconnect. Increased particle flux energizes comae, producing brightening and structural changes. Observational systems suffer too. Ionospheric turbulence degrades radio observations. Optical seeing worsens during geomagnetic storms. Scintillation creates apparent variability. In other words, during the highest interest window, the observing conditions were degraded. Some observed anomalies likely stem from solar-driven effects rather than from intrinsic comet behavior. Emerging display technologies complicate the epistemic landscape. Drone swarms with coordinated LED arrays and laser plasma demonstrations now create mid-air images visible across local regions. Satellite projection concepts remain limited by energy and atmospheric scattering. Large-scale bluebeam-style projections across continents stay impractical in 2025. However, localized synthetic spectacles achieve convincing effects for limited audiences. A well-timed display over a city might produce viral footage before instruments verify reality. Distinguishing natural phenomena from synthetic illusions requires multi-angle corroboration, cross-wavelength verification, and spectral analysis. Artificial sources often show spiky spectral lines tied to LEDs or lasers, whereas natural emission displays continuous spectra shaped by physical processes. The blue beam narrative exaggerates capability relative to engineering constraints. Possibility exists, evidence does not. The greater danger lies in corporate or political misuse of localized illusions and in the accumulation of small deceptions that erode trust. At length, the narrative arrives at a broader question: how to live with cosmic ambiguity. Some facts stand firm. 3I Atlas is verified. Meteor sightings occurred and hold physical signatures that demand analysis. Technologies from AI detection to drone projections are real. Solar orbiter data show the Sun behaves more chaotically than models predicted. Those items form the factual skeleton. Speculations populate the spaces between facts. Could perihelion outgassing seed debris that intersects Earth? Possibly, but unproven. Did AI misclassify mundane events and thus accelerate false narratives? That is plausible given known failure modes, though not proven for specific clips. Did synthetic skies produce convincing illusions in targeted cities? Technically feasible at limited scale, no proof of deployment in these incidents exists. The thought experiment about perihelion burns toward Jupiter rests on real physics but lacks confirming data. Faced with uncertainty, the culture needs responses. 4 approaches deserve mention. 1. Trust institutions and accept provisional authority. This fails if institutions hide errors or act opaquely. 2. Demand open data and integrate citizen analysis with professional verification. This empowers distributed review but risks overload and dissent. 3. Cultivate skeptical humility and accept not knowing without rushing to closure. This approach resists viral certainty but loses traction in an attention economy. 4. Embrace mystery as cultural value and permit wonder without premature explanation. Each approach has merit. The healthiest path blends elements from all four. Practical steps would help. Open data mandates for key astronomical sets would allow independent checks. Citizen science pipelines with quality control would harness global interest. Standardized provenance metadata for AI alerts would help downstream consumers evaluate confidence. Education in media literacy for transient phenomena would equip watchers to assess live footage critically. The stakes are concrete. Panic arrives when people believe institutions hide truth. Cynicism grows when corrections fail to dislodge first impressions. Exploitation blooms when fear becomes profit. Conversely, a literate public that tolerates uncertainty becomes resilient against manipulation. A shared culture valuing evidence and wonder together supports wiser decisions about exploration and response. Picture a pre-dawn when 3I Atlas slips past perihelion and begins its steady retreat. A comet tail arcs faintly. A scientist reads data and plans more observation. A pastor sees a symbol and offers counsel. A child sees a streak and feels simple wonder. Each response carries validity. The comet itself remains indifferent. Physics governs its path. When lights return to the sky, they will bring new puzzles. Instruments will improve. Quantum timing and distributed interferometry will reduce ambiguity. AI will flag more anomalies. The social environment will respond faster than ever. Our task is not to erase uncertainty. It is to build cultural tools to live within it. Demand evidence. Accept provisional conclusions. Preserve curiosity. Resist the urge to conflate thrilling questions with immediate answers. This narrative has followed the lights, sifted data, and mapped how culture transforms sight into story. It has measured real physics, instrument behavior, human error, institutional timelines, and the fertile imagination of online discourse. It has shown how the sun's politics, sensor quirks, algorithm decisions, and mythic frameworks together produce a sky that feels alive. For now 3I Atlas departs into the dark that birthed it. The meteors and spirals will continue. Technology will sharpen our sight. Culture will struggle with speed and certainty. The safest stance is clear. Hold the null hypothesis. Require independent verification for claims that overturn natural explanations. Celebrate curiosity and respect the patient, sometimes slow work of scientists who turn raw observations into reliable knowledge. Above all, remember that mystery does not imply malice. The universe remains indifferent. Our work is to observe with care, think with humility, and keep watching. Knowledge grows one verified frame at a time. After the green blaze faded from Moscow's sky and the comet turned its pale face from the sun, the world was left with questions that outnumbered answers. Yet this is how science has always moved, through unanswered questions that refuse to die. When people looked up in the nights following the event, they looked differently. Some sought reassurance in predictable meteor showers. Some searched for anomalies on live telescope feeds. Others simply wanted to know whether what they'd seen was real. The shared uncertainty became its own form of gravity, pulling scientists, journalists, enthusiasts, and storytellers into the same orbit. In laboratories and observatories, the slow grind of verification continued. Data from SOHO's coronagraphs were cross-checked against stereo imagery. Infrared readings from ground-based arrays in Chile and Hawaii were correlated with radio data from deep space dishes. The fragments of the Moscow bolide were tracked through infrasound signatures, confirming altitude and energy release consistent with ordinary meteoroids. Each dataset pulled the mystery back toward the domain of physics, away from the spirals of imagination. The work was meticulous. Analysts reconstructed atmospheric entry angles, modeled light curves, and compared them to known compositions. What emerged was a story of stone and metal meeting air at 70,000 km per hour, not of alien technology or divine warning. But the deeper truth lay in how easily public perception had diverged from those findings. Modern life connects everyone to the sky in real time, yet it also fractures consensus. In one browser tab, a peer-reviewed update explained the bolide spectrum. In another, a viral video claimed the same event proved planetary intervention. The same footage served two realities. One built on data, the other on interpretation. Institutions adapted slowly. NASA released visualization dashboards linking Meteor detections to verified sources. The European Space Agency opened portions of its telemetry archives for public inspection. Independent researchers built open-source models to reproduce observed trajectories. For a moment, transparency became fashionable, a defensive adaptation to the information storm. Meanwhile, 3I Atlas faded into the outer darkness, trailing a thin wake of dust invisible without instruments. For most telescopes, it became another entry in the archive, a line of numbers slowly receding from the sun. But the cultural wake persisted. Online communities continued to track its coordinates long after it passed beyond reach. The comet had turned into an idea, proof that something from another star could cross ours, and that we might notice. The post-event studies produced other dividends. Quantum-synchronized observatories in Japan and Europe achieved record-breaking coherence, demonstrating the first sub-nanosecond triangulation of a meteor. The result validated a prediction. With sufficient timing precision, atmospheric entries can be mapped as three-dimensional events in real time, their fragmentation captured like slow-motion sculpture. Data, not rumor, could finally match the spectacle. Artificial intelligence systems that once misclassified anomalies were retrained with this new corpus of verified cases. Developers inserted confidence gates and human review triggers for events exceeding statistical thresholds. By mid-2026, false alerts had dropped by half. Machines learned caution. So did their operators. The same period brought the first genuine test of synthetic sky detection protocols. A corporate art collective staged a drone-based display over Dubai's coast, projecting a luminous spiral that many mistook for a rocket launch. Within minutes, a distributed network of citizen observers cross-checked spectral data and viewing angles, proving it was terrestrial. The episode demonstrated that crowds, properly equipped, could self-correct faster than rumor could spread. It was a small victory for the open verification culture that had begun to emerge after the Moscow incident. Solar studies deepened too. With new polar data, physicists updated heliospheric models, incorporating chaotic magnetic behavior into predictions. The refined simulations explained several irregularities once labeled anomalous comet brightening. Under the new models, what looked like miracles became the signature of solar weather. The lesson repeated: strangeness fades under enough measurement. Yet some mysteries endured. A handful of events resisted neat classification, transients too brief, too faint, or too poorly triangulated to pin down. They became reminders that ignorance is not failure. It is the normal state of exploration. The sky has always been more complex than our capacity to measure it. By late 2026, the memory of the Green Night in Moscow had settled into collective folklore. It marked a hinge in how humanity watched the heavens. Before, people looked up expecting spectacle but trusting explanation. After, they looked up expecting uncertainty and still searching anyway. The shift was subtle but irreversible. Cultural responses diverged but matured. Some communities built educational networks teaching basic spectroscopy and image verification. Amateur astronomers learned to distinguish sodium lines from lead artifacts. Others founded data cooperatives linking backyard telescopes into distributed arrays that automatically uploaded footage for triangulation. The line between professional and citizen science blurred. Governments quietly adjusted communication protocols. Press offices began issuing tiered statements: preliminary, confirmed, and peer-reviewed. Each label carried timestamps and confidence intervals. It wasn't perfect, but it helped the public see that knowledge evolves instead of appearing whole. The speculative fringe persisted, but its influence dulled. When new lights appeared, more people checked databases before sharing theories. Curiosity survived, hysteria waned. As for Stefan Burns, his Project Dawn papers found modest readership in aerospace circles. They remained valuable not as revelation but as illustration how orbital mechanics could inspire public myth when detached from probability. His central idea, that a perihelion burn could redirect a probe toward Jupiter, became a classroom example in applied astrodynamics courses. Physics reclaimed what rumor had borrowed. Through all of this, one quiet theme emerged: precision breeds calm. Every improvement in measurement, from quantum clocks to AI filters, reduced the emotional volatility of discovery. The better we measured, the less room speculation had to grow. The green fireball, once an omen, became a case study in human cognition. By 2027, 3I Atlas had passed beyond Pluto's orbit. The last radio reflection from its tail returned weak and clean, confirming its retreat into interstellar space. It left behind no debris fields, no anomalies, only data and questions. What lingered was perspective. The event had forced humanity to confront the limits of its instruments and the elasticity of its imagination. It showed that the sky, for all its grandeur, remains subject to physics, and that our greatest uncertainties often arise not from what the cosmos hides, but from how we interpret what it reveals. In classrooms, students replayed the dashcam footage from Moscow and compared it with spectral charts. They learned that wonder and rigor are not enemies. In think tanks, policy analysts drafted frameworks for responsible AI use in astronomy. In religious halls, preachers invoked the same comet as a reminder of humility. And in homes everywhere, people still looked up, sometimes remembering the night the sky turned green. The difference was internal. They no longer rushed to choose between miracle and hoax. They allowed themselves the space between the quiet interval where data accumulates and understanding waits its turn. By the time the next generation of telescopes went online, watching the sky had become a form of literacy. Children learned to read it the way earlier generations learned constellations. Dashcam footage and sensor data fed the same open repositories. Every bright streak, every aurora, every comet tail arrived wrapped in metadata. Wonder and documentation had merged. Researchers could trace a meteor from its first plasma flash to the exact patch of interplanetary dust it came from. The same quantum-timed networks that measured its fall now guided spacecraft with centimeter precision. And still, the questions stayed larger than the answers. The public had changed, too. Forums that once traded rumor now compared spectra. Influencers invited astrophysicists instead of prophets. Even the thrill-seekers who chased anomalies did so with calibration charts on their phones. The culture had not lost imagination, it had learned to aim it. 3I Atlas remained a reference point, the case everyone returned to when debating how knowledge grows from chaos. Students replayed its timeline to study how a single night in Moscow forced humanity to build tools worthy of its curiosity. Teachers reminded them that the comet had never promised revelation, only reflection. By 2035, space agencies coordinated global sky drills, rehearsing responses to transient events much like earthquake drills on Earth. When an unexpected burst appeared over the Pacific, data flowed through the system in minutes. Within an hour, observers on 6 continents confirmed it as a natural bolide. No panic, no prophecy. Just process. Yet even in this age of precision, people still gathered outdoors to watch. On clear nights, families lay on rooftops, faces turned upward, the air humming with quiet talk. They spoke of past mysteries, of how fear once filled the gaps between facts, and of how those same gaps now invited collaboration. The night sky had become a classroom again. Somewhere beyond Neptune, 3I Atlas continued its long outbound glide. It carried no message, no intent, only the memory of a civilization that once mistook its reflection for a sign. The data it left behind lived on in the networks that learned to measure without myth. And so the story closed where it began, with light moving across darkness and humans trying to understand it. The cosmos remained silent, but no longer inscrutable. We had learned patience, precision, and perspective. The next time the heavens burned green, the world would not shout. It would watch, record, compare, and remember. Because listening, finally, had become our way of looking. Decades later, the green night over Moscow lived on not as warning, but as the moment when humanity learned to see clearly. The footage remained part of history lessons, the way Apollo landings once were. Students did not memorize dates, they studied the arc of discovery, how confusion became comprehension, how rumor gave way to method. The sky had not grown quieter. It never does. What changed was the response. By the mid-2030s, observation had become a shared civic ritual. Every region maintained local sky stations, compact observatories equipped with synchronized quantum clocks. The data they gathered flowed to open archives where anyone could analyze, annotate, and verify. The night sky was no longer owned by a few agencies. It belonged to everyone. Even the vocabulary shifted. Words like sighting and mystery lost their edge. People said transient or event. Headlines favored data over drama. The public's appetite for wonder remained, but it had matured. The need for apocalypse had faded. Governments, scientists, and citizens formed a network known simply as the Array. It spanned 5 continents. Each station, some professional, some backyard, contributed to a real-time sky map updated every few seconds. The map was not just science, it was art. A living tapestry of movement, meteors, satellites, auroras, plasma waves flowed across enormous public screens in museums and plazas. You could stand before it and watch the breathing of the solar system. The Array did more than track light. It built trust. During its first major test, a series of brilliant green meteors entered Earth's atmosphere over the Indian Ocean. The color and timing resembled the Moscow fireball years earlier. Within an hour, the Array correlated footage, triangulated trajectories, and confirmed the cause: debris from a small asteroid intersecting Earth's orbit. No panic, no speculation. The event ended with applause at watch parties instead of fear. Trust changed what curiosity looked like. When people no longer feared deception, they asked better questions. They debated data quality instead of motives. They competed to interpret spectra, not to invent conspiracies. The collective gaze sharpened. In a lab on the outskirts of Geneva, an astrophysicist named Ilyana Kirov refined the legacy of 3I Atlas. She developed models of interstellar dust interaction based on its data. Her work revealed that fragments of other star systems cross ours far more often than anyone had realized, tiny, silent, unnoticed. Every month, grains of alien worlds rained through the atmosphere. Some burned unseen, some settled in oceans. The boundary between out there and down here blurred. Kirov's models inspired a new mission, Project Threshold, a fleet of autonomous probes designed to intercept interstellar dust and analyze it before entry. Each probe was the size of a suitcase, fitted with quantum clocks, AI navigation, and miniature spectrometers. Launched from high-altitude balloons and orbital platforms, They listened for faint anomalies, temperature spikes, micrometeor impacts, minute shifts in background radiation. One day in 2038, a probe detected something strange, a cluster of particles moving in tight formation, maintaining relative spacing over thousands of kilometers. The array confirmed it across multiple stations. For a moment, the old thrill returned. The world held its breath. But caution prevailed. Teams checked calibration, ruled out sensor drift, and compared with space weather models. Days passed. Weeks. The pattern persisted but eventually resolved into a mundane explanation: charged dust trapped in a magnetic flux tube shaped by the solar wind. Not artificial. Not mysterious. Just new to human perception. The episode reaffirmed the creed of the post-Atlas era: wonder without hysteria. The discovery still made headlines, but the tone was steady. Solar magnetic filament captures interstellar dust, read the caption under a composite image glowing in infrared hues. That restraint, that careful awe, became cultural identity. Artists found beauty in measurement itself. Poets wrote about precision. Children grew up knowing how to interpret data plots as easily as constellations. School competitions awarded prizes for identifying false positives in sky reports. The mythology of the cosmos did not die, it evolved. Where gods once threw fire, algorithms now translated light into meaning, and people felt reverence for both. Meanwhile, far beyond Pluto's frozen reach, 3I Atlas continued its journey. Decades of solar radiation had reshaped its surface. Its volatile gases were gone, its nucleus hardened into rock. Telescopes no longer saw it. Only simulations kept its path alive, tracing its slow escape into the thin void between stars. In 2042, an outbound deep space probe named Kepler Sentinel-2 passed through a region of space where Atlas had once traveled. Its instruments detected faint dust particles with isotopic ratios matching the comet's recorded spectra. It confirmed the object's fading trail, the last physical sign of its passing. Scientists called it the ghost tail. That confirmation closed the chapter. 3I Atlas was real, natural, and gone. But the culture it catalyzed endured. The array continued to expand. New stations on the Moon provided polar coverage. Mars bases joined the network, giving parallax data across interplanetary distances. Humanity had built a solar system-wide sensory organ, a distributed consciousness of observation. By mid-century, the line between exploration and introspection blurred completely. Astronomy was no longer about what lay beyond. It had become a mirror of how humans handled the unknown. During one symposium, an old researcher summarized it best. The universe didn't change. We did. The cosmos was always transparent. Our eyes were the cloudy part. That sentence outlived him. It became etched above observatory entrances and printed on the array's digital dashboard. The next great spectacle came without warning, a flare from Proxima Centauri that painted Earth's magnetosphere in rare colors. For 3 nights, auroras reached the equator. Cameras caught ribbons of violet and white swirling over deserts and oceans. This time, people didn't fear the light. They went outside, recorded spectra, posted data in real time, shared calibration files. Entire cities glowed with reflections of the aurora on windows and screens. It was chaos, but the organized kind, a symphony of observation. Amid that beauty, a journalist recorded a simple interview with a child holding a spectrometer app. "What are you looking for?" she asked. The child smiled and said, "For what we don't know yet." That phrase spread as fast as any rumor once did. It became a motto for an era. In the decades that followed, this ethos extended to every frontier: biology, climate science, artificial intelligence. The discipline learned from the sky spread everywhere: check, confirm, wait, share. The fear of not knowing had been replaced by the courage to keep asking. And still, on certain clear nights, people stood outside and looked up, half hoping to see another visitor from between the stars. They knew it would come, someday. Another comet, another mystery. But when it did, they would not panic. They would measure, listen, compare, and welcome it with quiet respect. Because the true legacy of 3i Atlas was not data or debate. It was the realization that curiosity, disciplined by patience, can turn fear into understanding. That the sky does not divide us, it connects us. That uncertainty, properly faced, is not a void. It is the beginning of knowledge. By the middle of the 21st century, people had stopped treating the sky as background. It was a system, alive with data, constant in motion, transparent in meaning. Every major city maintained public observatories, free to use, linked to the global array. Even the smallest villages had sky nodes, simple instruments pointing upward, recording spectra and time-stamped events. Together, they formed the largest collaborative project in human history. The network changed daily life. Weather forecasts now included meteor probabilities. Schools organized sky shifts where students monitored data streams as part of classwork. Transit screens displayed aurora alerts next to flight schedules. The universe had been folded into routine. And yet, amid all the precision, mystery persisted. In the spring of 2047, a faint object appeared beyond Neptune. Its light curve pulsed irregularly, not fast enough for rotation, not slow enough for comet outgassing. The array tracked it for weeks before consensus formed. It was natural, an interstellar body smaller than 3i Atlas, tumbling end over end. The confirmation came quietly, without panic or prophecy. Newspapers called it the second stranger. The public followed its journey with calm fascination. People watched live telemetry as if it were a sport. Artists turned its slow drift into sound installations. The world no longer demanded answers overnight. It had learned to live with questions measured in orbits. That patience was tested later that year when a burst of blue light illuminated half the southern hemisphere. Satellite feeds lit up, sensors triggered across continents. The first assumption was solar activity, but the sun was quiet. Data analysts across the array scrambled to cross-check readings. Within 2 hours, the cause emerged: a fragment of the second stranger had struck Earth's upper atmosphere at a shallow angle, vaporizing over the ocean. It left a brief electric glow, then vanished. No one called it invasion. No one called it divine. It was catalogued, studied, understood. The incident barely trended online. Humanity had achieved the rarest state in history: collective composure. In the years that followed, observation expanded beyond light. Gravitational wave detectors joined the array, their data mapped in the same interface. People could see the tremors of distant collisions ripple through space-time like wind through wheat. The cosmos was now audible. Communication evolved too. Instead of breaking news, observatories issued event symphonies, visual and sonic renderings of data compressed into seconds. A solar flare sounded like a slow drumbeat, a meteor shower resembled rain. Science had become sensory. Amid this abundance, philosophers asked what had changed. The sky still threw stones and fire, the sun still flared, comets still came and went. The difference was psychological. Humanity had learned to think on cosmic timescales. Panic had a half-life now. The memory of the Moscow night endured in a small museum built near the site of the original sightings. Inside, a continuous loop played the green fireball footage beside the spectral graphs that had explained it. Visitors stood quietly, watching the two versions of truth, the emotional and the empirical, side by side. Outside the museum, an inscription read, "From wonder came understanding. From understanding came peace." By the 2050s, the array's reach extended beyond the solar system. Miniature probes, propelled by light sails, carried quantum-linked clocks and cameras into interstellar space. They transmitted back faint images of dust clouds illuminated by distant suns. The first of these, Sentinel-3, returned data showing a faint trail, the dying echo of 3I Atlas, still drifting toward the dark between stars. For many, that felt like closure. The object that once embodied fear had become a marker of how far humanity had traveled, both physically and mentally. On the 50th anniversary of the Moscow event, a global broadcast connected every observatory on Earth. Screens filled with live footage of the night sky, stitched into a single panorama. Tens of millions watched as the data rolled in spectra, timestamps, coordinates. There were no speeches, only a quiet voice repeating one line. "The sky is watching back." Then, for a brief moment, a small meteor flared green across the shared feed, as if the cosmos itself remembered. No panic, no prophecy, only applause, laughter, and the sound of people breathing in sync across the world. That was the legacy of 3I Atlas. Not a revelation, but a rehearsal. Not an ending, but a new discipline of attention. The human species had learned to stand under the universe without trembling, to watch without worship, to question without fear. And somewhere, beyond the reach of any telescope, another wanderer turned toward the sun, unseen for now, already on its way. By the late 2050s, the sky had become the most democratic mirror on Earth. Every person with a lens, a sensor, or a patch of open sky was part of a network that never slept. Data flowed across continents in quiet constancy. The universe no longer waited for professional eyes. It revealed itself to anyone willing to look with discipline. The transformation reshaped culture. Film studios released verified fiction, cinematic stories built entirely from real astronomical data stitched into narrative. Musicians composed with the frequencies of pulsars. Architects designed buildings aligned with orbital nodes, so sunlight and shadow traced the movement of planets across facades. Science was no longer separate from art, it was its foundation. In classrooms, children no longer memorized constellations by name but by spectrum. They learned to interpret color shifts and emission lines, to translate physics into intuition. The night sky, once a source of myth, had become a shared literacy. And yet, beneath the clarity, one truth endured: certainty never lasts. In 2062, one of the array's deep space sensors detected a rhythmic signal near the Kuiper belt. It wasn't a message, just a pulse, perfectly regular, repeating every 11 minutes. For 6 months, no instrument could explain it. Theories ranged from a tumbling object reflecting sunlight to a binary microasteroid pair eclipsing each other. The pattern persisted, calm and indifferent. Unlike earlier generations, people didn't leap to cosmic conclusions. They logged, cross-checked, waited. The signal faded the following year, explained eventually as interference from a fault in one of the sensor's quantum amplifiers. But the story became a lesson, not a scandal. The unknown had returned for a brief visit, and humanity had greeted it with patience instead of fear. Out of that episode came a new discipline called cultural astronomy. It studied not stars, but how societies reacted to them. Its students examined the chain of events that began with 3I Atlas, the panic, the speculation, the slow correction, the rise of collective calm. Their thesis was simple: civilizations mature when they learn to coexist with uncertainty. In one of its early lectures, a scholar named Amorajani projected the first recorded green fireball over Moscow alongside a modern event from 2061, two near-identical streaks separated by almost 4 decades. The difference, she told her students, is not in the sky. It's in us. The cosmos repeats its lines. We decide how to read them. Her words echoed around the world, quoted in documentaries, carved into observatory walls. Humanity had found its posture upright, steady, looking outward with a kind of quiet confidence. By 2070, interplanetary traffic was routine. Cargo drones moved between Mars, Ganymede, and Earth orbit on predictable schedules. The array had expanded across those worlds, its nodes synchronized by quantum timing. For the first time, humans observed the same meteor shower from 3 planets simultaneously. The data revealed parallax shifts so subtle that they exposed the curvature of the solar system's gravitational field in visible form. The discovery wasn't dramatic, but it was beautiful. It showed that perspective, literal and philosophical, was humanity's new tool of survival. Even in space, old instincts flickered. When an outbound freighter near Jupiter reported a faint, green glow along its trajectory, the crew laughed and named it Atlas's Echo. The glow turned out to be plasma from solar wind interacting with metallic dust. Routine physics. Yet the name stuck, a cultural relic carried forward with affection rather than fear. Meanwhile, the sky over Earth grew busier. Satellites moved in orderly arcs, visible to the naked eye as constellations of slow, deliberate stars. Kids learned to tell which dots were human and which were not. And through it all, people still looked up for no reason other than wonder. One summer night, a group of students camping in the highlands recorded a new kind of aurora. It rippled in sharp geometric lines, almost architectural in form. Data from the array confirmed it as a rare magnetic standing wave, natural, complex, precise. The footage went viral, but not as shock or prophecy. It spread as joy. The comments under every post said the same thing: the universe is teaching us geometry. By then, few remembered what panic felt like. Fear had been replaced by curiosity, superstition by symmetry. The world had learned the slow rhythm of verification. Every anomaly was an invitation, not an emergency. And so, in 2081, when another interstellar visitor was detected, this one darker, slower, quieter than 3i Atlas, the announcement made headlines, but not hysteria. Observatories coordinated instantly. Datasets merged. Artists began designing commemorations before the comet even reached the inner solar system. The phrase "another traveler" replaced omen. People gathered in plazas to watch its faint reflection through projection domes, not with dread, but with gratitude. They called it Visitor B. Children pointed at its faint line across the stars, their parents explaining how its light had traveled for millennia to reach them. This time, no one argued online about meaning. No one claimed divine prophecy or hidden agendas. The story belonged to everyone, owned by no one. As Visitor B curved past the sun and faded outward, scientists updated its trajectory, artists recorded its passing in color and sound, and citizens across the planets quietly celebrated the fact that, once again, they had understood. The journey of 3i Atlas had ended long ago, but its echo remained everywhere, in the architecture of observatories, in the tone of news reports, in the measured awe of every upward glance. It had taught a species to replace certainty with attention. And even in silence, the universe continued to speak. Each flash, each trace of plasma, each ripple in the aurora whispered the same truth: that the cosmos is neither enemy nor oracle. It is a mirror. And the light we see there is the reflection of our own awakening.